For Lab 3, we observed the motion of a star whose data was provided in a CSV file, and from that information, finding the mass of the black hole the star is orbiting. Through the application of Newton's gravitational force principle, along with the different net force components and the change of momentum components, we were able to determine the mass of the black hole, which we determined to be 2.0869 10 to the 31st kilograms. There are a few principles that pertain to this lab, including the momentum principle, which is dp over dt equals the net force, which also means the change of momentum over the change in time. Also, Newton's law of gravitation, which is where the force of gravity equals negative g, which is the gravity constant valued at 6.67 times 10 to the negative 11th newtons times meter squared over kilogram squared, times the mass of object 1, in our case the star, times the mass of object 2, the black hole, divided by the radius squared times r hat. Next, we have to set up the code. First, we have to plug in the given data from the lab, including the star mass, black hole position, and delta t. We import the position data from the CSV file, then in the first while loop, we make Python calculate the velocity of the star on its trajectory orbiting the black hole. In the second while loop, we find v initial and v final, and from this we can find p initial and p final. That is just the mass times the velocity. From this we can find delta v and delta p. We know that the net force of an object can be broken down into parallel and perpendicular forces. Here, dB dt is given as a change in momentum over change in time, and net force is equal to dB dt. We know this because of the momentum principle. Then we find the direction of momentum, here. We do this by dividing the initial momentum by the magnitude of the initial momentum. Then we find the magnitude of dB/dt parallel because it is the change of magnitude of momentum over delta t, here. Then we multiply that by the direction, or p hat. Here we get the fact that Fnet parallel equals dB/dt parallel. Then finding dB/dt perpendicular is simply dB/dt minus dB/dt parallel, because dB/dt parallel and dB/dt perpendicular summed together equals dB/dt. Then Fnet perpendicular will equal dB/dt perpendicular, as you can see here. Finally, we're able to find the mass of the black hole by first defining the gravitational constant, then manipulating Newton's universal gravitation principle to calculate the mass of the black hole. We do this by multiplying the magnitude of Fnet by the magnitude of the star's position minus the black hole position squared, all divided by the star's mass times the gravitational constant. Now, when we run the code, you can see the yellow arrow is the net force, while the blue arrow is the perpendicular component of net force, and the black arrow is the parallel component of the net force, as the star rotates around the black hole. The mass of the black hole will be printed in the window here, as our code directed. Now, what does it mean? I'm going to discuss how Fnet perpendicular, and Fnet parallel are different from delta p over delta t over delta t perpendicular, and delta p over delta t parallel are different. Now, a force, mass multiplied by acceleration, causes, or rather is the change in momentum over the change in time. Momentum can be broken down into mass and change in velocity over change in time, which is the definition of acceleration. Therefore, forces parallel to the direction of motion will cause a change in the magnitude of the momentum, while forces in the direction perpendicular to motion will cause a change in direction. In essence, these are not different. Fnet equals delta p over delta t times mass, and so on and so forth for the rest, as we have already used in this lab. What if? Basically, can we find a different mass? No. There would be no way to find a different mass from the one we already calculated if the black hole was in the same position, because the mass we found was dependent on the distance from the star's mass, and the forces acting on the star. Since all of these are unchanged, the mass of the black hole, the only variable left, will be unchanged. So, all in all, using the momentum principle and Newton's universal law of gravitation, we were able to find the mass of the black hole, which came out to be 2.0869 10 to the 31st. Also, force and momentum can be broken down to parallel and perpendicular forces, and the only mass to be found is the one we already found.